And oh, this sounds better. All right. So we have seen this example which tells us that if we want to verify controllability of the unknown truth system, we do not need data to be informative for system identification. Let's go through the proof or parts of the proof of the theorem to give a flavor of type of arguments used. Well, if part is easy again. If this matrix has full row rank for all lambda, I can take one data consistent system, an arbitrary one. Then I know that this linear equation is satisfied by the definition of data consistent systems. Now, if I add both sides minus lambda times x minus, I can write the right-hand side in this way, which tells me, since this is full row rank, which tells me that this matrix must have full row rank. And then by the how-to test, then AB is controllable. This is the easy part. For the only if part, I will assume that all data consistent systems are controllable, and then I want to show that this matrix has full row rank for all complex lambda. Okay. So all data consistent systems are controllable, and my goal is to show that for arbitrary lambda and arbitrary complex vector z, z conjugate transpose this matrix equals 0 implies z is equal to 0. Or in other words, this matrix has full row rank for any lambda. Okay? So I'm going to look at the case where lambda and z are real, and non-real case is similar, but it takes more space, so I skip it. It is in the lecture notes. But the main idea is here in the real case. So now I take a real lambda and a real vector z such that norm of z is 1. Okay? And I assume that this relation holds. Z transpose times this matrix is 0. Okay? I take an arbitrary pair, AB, data consistent. What I know is that this AB is controllable because all of them are controllable. Now, if I look at Z transpose x plus minus lambda x minus, I can replace x plus by A x minus B u minus, and there is the minus lambda x minus part. So this expression is equal to this one, and it is 0. Okay? What does that mean? Now, if you look at this expression, I have Z transpose times A minus lambda I, so it is here. and Z transpose B times U minus, so it is here, right? If I look at this expression then, these Z-related terms are going to cancel out because of this relation. Therefore, I'm going to look at A times X minus plus B times U minus, and it is X plus. Because AB is in the data consistent set. So this is X plus, which means that this pair is another data consistent system. Agree? I started from a data consistent system, AB, and data consistent means that, oh, this is Hank from yesterday. And this is the definition of data consistent system. AB data consistent means that this linear equation is satisfied. So I take one of them using the property that Z transpose is a left annihilator of this matrix with lambda. I came up with another one. So this new A, this new B is another data consistent system. Right? So this pair is another data consistent system. Okay? Therefore, it must be controllable because all of them are controllable. Let's look at now Z transpose times this new A. Well, Z transpose Z is 1. Right? Therefore, this is going to be equal to lambda times Z transpose, because I have Z transpose A here. Z transpose Z, Z transpose A is going to be also Z transpose A, so they cancel each other. And then I have minus minus plus lambda Z transpose. Which means that lambda is an eigenvalue of this matrix. Okay? Let's look at Z transpose times B new B. Well, Z transpose Z is 1. Therefore, this thing is going to be 0. What does this tell us? Well, because of Hart's test, it says Z must be 0 because this pair is controllable. If Z were not 0, we would contradict controllability. But Z0 is contradiction because Z transpose Z is 1. Therefore, we prove that this implication holds. So this matrix X plus minus lambda X minus must have full row rank for any lambda. Okay? So this is a necessary and sufficient condition for informativity for controllability. If lambda happens to be a non-real number, then there is a similar construction here, which is a little bit more complicated, and it is because of the fact that when I defined data consistent systems, I didn't write it explicitly, but I consider only real matrices A and B. The similar construction with complex Z and lambda would work, but yield complex matrices, which I do not consider as data consistent. So if lambda and Z are non-real, there is a way to generate data consistent systems, real matrices, huh? But it's a little bit more complicated than what is it on the slide. Okay. Now, here is the question. Well, how to test is about finitely many lambdas, eigenvalues of A, at most n, if A is n by n matrix. Whereas this test requires checking full row rank of this matrix for every complex number lambda. Huh? Well, there seems to be a way to make it finite. I'm not going to prove it, but we can prove that the data are informative for controllability if and only if X plus has full row rank, and this matrix has full row rank for all mu eigenvalue of X minus X plus dagger, a right inverse of X plus. And you can see at least A from the theorem very easily, because if this has full row rank for all lambda, in particular, for lambda to be 0, it has to have full row rank. And in that case, X plus must be full row rank. Huh? And the rest is, the rest follows from simple algebraic manipulation. Okay? So now, this is finite now, because I can first check whether X plus is full row rank. If not, end of the story. If yes, I find the right inverse, find this matrix, find the eigenvalues, and check this rank condition on the eigenvalues. It is legitimate then to call this as data-driven Hartus test. Huh? Well, once we studied controllability, I can define the similar concept for stabilizability, informativity for stabilizability. All AB pairs need to be stabilizable, and then I very similarly can prove this theorem that stabilizability is necessary and sufficient condition for informativity for stabilizability is that this matrix must have full row rank, not for all lambda, but for all lambda outside the open disk. Okay? And again, one can make it a finite, one can come up with a data-driven Hartus test. It is a little bit more complicated, but essentially it is the same idea. And again, also for stabilizability, one doesn't need identifiability. I can, if the data are informative, I can guarantee stabilizability of the true system, even if I cannot identify it. Okay? Any questions? How much time do I have still? One hour. Okay. Because I am halfway through. Half an hour wouldn't be enough. All right. But I think I have enough material to cover an hour. So far we have seen stability for autonomous systems and controllability for input state systems. Okay? let's look at stability again, but not for autonomous systems, for input state systems. So this is the setup again. I have a true unknown system, ASPS. I collect data from input state data from this system. I write the set of data consistent systems. And this time, I am interested in informativity for stability of input state data. If it were only state data, I already know the answer. But this time, I have also input data together with state data. Well, I'm not going to prove every single statement, by the way, because it would take very long. But I want to give a flavor of different types of properties. Then one can prove that the input state data are informative for stability if and only if x minus has full row rank, and there exists a right inverse of x minus such that x plus, x minus dagger is stable and u minus x minus dagger is 0. If these conditions are satisfied, then A is uniquely determined by the data, but B may not be uniquely determined by the data. So basically, this theorem says for stability in the input state data case, one can verify stability without being able to identify the system again. Because we have more data, we have also input data. So it is in contrast to only state data situation. And if we remember the condition for identification in the input state case, it was x minus u minus having full row rank. And as you see, this doesn't need to be the case for informativity for stability. Only x minus needs to be full row rank. And you see that there are more properties than controllability for which we can guarantee the property, although we cannot identify the underlying system. At least for controllability and stabilizability and stability, we established that. But these are all, of course, analysis problems. Okay? If we continue with analysis problems, we studied controllability, why not observability? So now I change the setup to state output data. I have state output system, no inputs. N is the dimension of states. P is for the outputs. I have a true system in this model class given by matrices AS and BS. These are unknown. I collect data, let's say state data and some output data. I write the data then they have to satisfy these relations with respect to AS and BS. I then write down the data consistent systems. These are all CA pairs satisfying this linear equation. You see, we can deal with pretty much anything. You can write down these things. Whether they lead to something interesting or not is another question, but we have a framework in which we can formulate all sorts of problems. Okay? Any questions here? Then, I know that the true system is one of the data consistent systems. What about system identification in this case? Whenever I change the model class, the type of the data, there is another system identification problem. Okay? Well, one can show that also it's clear from here because AC are the unknowns. This has a solution, but it can have a unique solution only if and only if X minus has full row rank. So system identification is going to boil down to X minus having full row rank. Okay? What about observability? I'm going to say that the data state, output data are informative for observability if all systems in the data consistent set are observable. It turns out that so the conditions require identifiability already. Without being able to identify the system, you cannot decide observability. Now we are looking at analysis problems, stability, controllability, stabilizability, stability for input state, observability for input, state output data. And let's make a summary of it. So here are the properties I have looked at. Here are the model classes and data types. And here are the conditions. Among these 1, 2, 3, 4, 5 properties, the first one and the last one require identifiability, and the middle ones do not require identifiability. So basically, whether identification is necessary or not depends on the problem you have. For certain problems, you need identifiability. For certain other problems, you do not need identifiability. Okay? But of course, especially engineers, I am an engineer, by the way. I'm a professor of mathematics, but I studied computer engineering long time ago, almost before. I never had a personal computer while studying, for instance. The first laptop I bought was many years later, so it was long time ago. But I am an engineer. I don't have any diploma from mathematics, but I am a failed engineer because I became a professor of mathematics. And if you look at from the other side, maybe it's not such a big failure. Okay. And so let's think of from engineering point of view. It is nice to have this theory for which we can check properties, but it would be even nicer if we can design controllers. And that's the ultimate goal anyway, right? All these properties we study with the goal of designing controllers. Otherwise, themselves, they are not interesting that much. Now let's look at now some design problems. Now I'm going to look at input state systems, models of, well, it's not on the board, but given by AB matrices. Again, I have some data, input state data, and I write a set of data consistent systems. And ASBS, the true but unknown system, is one of them. Okay? Now I'm going to say the data are informative for stabilization by state feedback if there is one feedback gain, k, such that a plus bk is stable for any ab consistent with the data. If the data, is it done? If the data are informative for stabilization, then I don't care whether I can identify the system or not. It may require identifiability, I don't know. But nevertheless, I can come up with a stabilizing controller for that unknown system. Some part of the question is not there. Oh, sorry, no, it's there. So now the question, this is an interesting question. We have studied stabilizability with input state data. In the model-based theory, we know one thing. Actually, it's the definition of stabilizability, right? A system can be made stable by a state feedback if and only if it is stabilizable, right? So what about the data-based version of that relationship? In the model-based version, stabilizability and stabilization by state feedback are the same. Is it true also for data-based theory that if I have informativity for stabilizability, then immediately I have informativity for stabilization by feedback? Sorry, I move my hands too much. So is it enough? Here is an example. Look, I take the simplest possible case. One state, scalar input. I look at this very simple data. Now, x minus is 0, x plus is 1. If I look at if I look at x plus minus lambda x minus is 0, so this is going to be 1. So it has full row rank for any lambda. So the data are informative for stabilizability. Any data consistent system is stabilizable. Okay? But if I look at the data consistent systems, they are systems of this form. And in particular, -1, 1, and 1, 1 are both data consistent systems. But there is no single feedback, k, which stabilizes both at the same time. Because if there were, then that would mean that -1 plus k and 1 plus k are stable at the same time. But that's not possible. If k is positive, 1 plus k is going to be greater than 1. If k is negative, minus 1 plus k is going to be in magnitude greater than 1. And if it is 0, it's not stable anyway. So informativity for stabilizability does not imply per se informativity for stabilization by state feedback, unlike the model-based theory. Okay? That's one thing. Okay, let's continue. So this was the definition. Now, how can we characterize it? Well, here's the characterization. Data are informative for stabilization by state feedback if and only if X minus has full row rank and there exists a right inverse X minus dagger such that this X plus X minus dagger is stable. Two very quick observations. One, it doesn't say X minus U minus must have full row rank. Therefore, even if I cannot identify the system from data, it may be possible that I can find stabilizing controllers. That's very cool. But what is not so cool is that the second condition is not easy to verify because it says there exists a right inverse, but there are infinitely many. How can I verify that for one of them this condition is satisfied? It's not super friendly, at least as it is now. Okay? But let's look at an example again. So, two-state, one-input system. This is the X data. This is the U data. I look at X minus, X plus. Well, X minus happens to be a non-singular matrix. Therefore, it has full row rank. Its right inverse is unique because it is non-singular. And if I make this calculation, X minus times the inverse of X minus, I obtain this matrix, which turns out to have these eigenvalues, and you can easily see that they are in the open unit disk. When I say you can easily see that, I don't mean that I can easily see it, but I trust I trust you more than I trust myself. I'm too old, but I'm sure young people immediately see it. That is, they are in the open unit disk. So I can stabilize this system. And if I look at data consistent systems, though, any system of this form is data consistent. There's no way that I can identify the system. And not even some part of it, like the controllability example. I can't, none of the entries I can identify. Okay? But if I take this K, it stabilizes all of them. But this is really cool now. Because it is not about some properties of controllability, stability, and so on. It is about designing controllers. There is a true unknown system. I collect data from it. Even if I can't identify the underlying system, I might be able to, if the data are informative, I might be able to design a stabilizing controller for that unknown system. Right? So that is something nice. Okay? This is the last proof of today. Yes? Question?
Previous class we said about some similar kind of methodology for stabilizing a system using feedback control. So how that result and this result are different, or?
They are different in the sense that there is an assumption already there that the input is persistently exciting, which means that you can identify the system if you like. But instead of identifying the system, you use that fact persistence of excitation, and also parameterization of all trajectories to solve a certain control problem.
So for
But
this case, probably whatever k we are getting, that would be able to characterize, would be able to stabilize all the systems inside that schema T.
yeah, yeah, it does. If you apply this feedback, let's apply this feedback actually, and then you will see that this is going to be the whatever AB does not matter. This is going to be the closed loop system. So there is maybe I should have mentioned it. In the proof, it is going to be clear, but at this stage, I should have mentioned it. If it is possible, if the data are informative for stabilization, then A plus BK does not depend on the choice of AB. So it is a unique matrix. In this case, it is going to be this matrix. Whatever system you take, apply this feedback, and then this is the closed loop system. Any other questions? Yes. What do you say? If you choose? Yeah. Sure.
Then only A is left.
Sure.
But then that A should be stable.
Yeah. Let's do it. What do you want to choose? I am taking a risk here, because if there is a golden rule of mathematical presentations: never compute in public. Never compute in public, because you can make yourself ridiculous. But let's do it. Yeah, you get that matrix, right? For any AB, you would get that matrix.
But then there is one point. We are not able to fully choose the eigenvalue.
That's a good point, because I am not interested in that. If I define such an informativity problem, I assure you, still it is not going to require identifiability. What it is going to require is that this matrix has eigenvalues, whatever you specify.
But I think previous class approach, we would able to only stabilize a single set of single system. Or in last lecture.
Last lecture, yeah?
Yeah. So we are stabilizing a set of systems with same data.
Yeah, but that would be a bit misleading to think that there was one single system there. We have a set of systems here, because as long as you apply a persistently exciting input, this set of data consistent systems is going to be a singleton. So that is because of the choice of the input, or the approach one takes. But you see, if at all we are interested in a database systems and control theory, I mean, it may happen that some people are not interested in. But this is the way to continue, because then I know what we can achieve, what we cannot achieve. If I start with persistently exciting input, I do not know what I can achieve. I already made an assumption. But here I figure out what is necessary, what is required to solve a given problem. Okay? All right, now, I want to prove it. It's a little bit dense, but let's go, and we are all tired. I am tired. I can imagine you are also tired. But let's put a collective effort, because this is the last proof of today. The rest does not contain any proof, and probably the most interesting one at the same time. Okay? So now, for the if part, if these two properties hold, I want to show the data are informative for stabilization, which means that if I want to show that there is one K that stabilizes all data consistent systems. So I take an arbitrary system, AB, and I want to find a K such that A plus BK is stable. Okay? So the first thing I do is I write the defining property of being data consistent. So these linear equations are satisfied. Now, because of B, I know there exists a right inverse such that this matrix is stable. I multiply both sides from right by that right inverse. And here, on the left-hand side, I have a stable matrix. On the right-hand side, I have this matrix. Huh? But look at this term, U minus X minus dagger. That does not depend on the choice I made here. I have chosen one system. U minus X minus dagger depends on the data only. Huh? And if I choose it as K, as my gain, then I'm done. Huh? If I choose K to be U minus X minus dagger, but a particular one, that's a stabilizing feedback for all AP. And then we are done. Okay? Well, as I said, this is always typical. One side is very easy to prove, and the other side is, the other implication is more difficult. So necessity is, again, difficult. Now, what I know from the fact that data are informative, that there exists a K such that A plus BK is stable for all AB in sigma. And I want to now, on the basis of this, prove that A and B hold. If I look at A, it requires X minus to have full row rank. And B, this stability. First, I do the following. I take a data consistent system, AB. And I take something like A0, B0. These are also matrices of the same size as A and B. With this property, namely the rows of this matrix are left annihilators of X minus U minus matrix. Okay? Now, if I look at the defining relationship, AB needs to satisfy these linear equations. But therefore, since A0, B0, X minus U minus 0, this matrix times X minus U minus must be also still X plus. Which means that this new pair is yet another data consistent system. And this is true regardless of the value of alpha. So for all alpha. Now, I do the following. If you look at this relationship, if I multiply this thing from left by any matrix, the right-hand side is going to be still 0. So I multiply it by, oh, there is an awful typo here. So it shouldn't be, the transpose shouldn't be on top of K, but it should be on the parentheses. So it should be A0 plus B0 K transpose. Okay? Sorry about that. I will correct it after the lecture. Okay? And so if I multiply by this transpose of this matrix, then it is still 0, which means then that this pair is also a data consistent pair. Right? Agree? And it's for all alpha. But I do know that there is this K which stabilizes any AB pair in sigma. And in particular then, it should stabilize this pair. Now I take this new A, new B, and write new A plus new B times K. And that is this expression. Okay? And for any alpha, this M alpha matrix needs to be stable. Agree? Now, let me denote the spectral radius of a matrix M by rho M. Spectral radius means the maximum of the magnitudes of the eigenvalues. So here it is the definition. Now I look at M alpha divided by alpha. So I divide this by alpha, and then this alpha disappears. And the spectral radius. Since M alpha is stable, spectral radius needs to be less than 1 for any alpha. If I take the limit alpha tends to infinity then, this expression needs to tend to 0, because M alpha, spectral radius is less than 1. 1 over alpha, alpha tends to infinity, goes to 0. If I look at the limit of this thing divided by alpha, alpha tends to infinity, I obtain this expression. Again, the transpose is on the parenthesis. So I have here a matrix transpose times the matrix, and it is spectral radius is 0. Now this is a symmetric matrix, semi-definite matrix, spectral radius is 0. This can happen only if the matrix itself is 0. And so, therefore, for any A0, B0 with this property, A0 plus B0 K needs to be 0, where K is a stabilizing feedback. And from that, we see that this implication holds now. Whenever A0, B0 kills X minus U minus from left, it kills identity K from left. But now, some of our colleagues like to drop names from Roche-Capelli. What was it? Roche-Capelli theorem. It follows, no, it's a basic elementary fact from linear algebra that if this holds, identity K must be equal to X minus U minus times some matrix, let's say F. And if it is so, if you look at the first row block, identity is equal to X minus F, means that X minus has full row rank, and F is a right inverse of X minus. And then from the second one, we also see that this X plus times F is A plus BK, and that is stable, which proves first A and then B. Okay? Any questions? But now I have a question. It is nice, but is it useful? Forgetting about practical issues, is it useful from theoretical point of view? It's not so useful because it says there exists a right inverse. Huh? How am I supposed to check these conditions? If the inverse is not unique, then there are infinitely many inverses, right inverses. And I have to find one such that x plus times that right inverse is stable. And that is not an easy problem. So we have to do something for that. Well, one can actually come up with linear matrix inequalities which are going to replace these conditions A and B. I'm not going to prove these statements, but one can prove that informativity for stabilization by state feedback is necessary and sufficient for theta, existence of theta, satisfying these linear matrix inequalities. And if they are satisfied, then this is a stabilizing feedback. So now it is much more computationally friendly. If somebody enters this room, I open my laptop, run my favorite software to solve linear matrix inequalities, and then solve these ones. But there is a catch still. Look at the dimension of theta. Theta has t rows, so this is the number of data samples, and n columns, that is the system dimension. So if you have a very large data set, the number of unknowns is very large, because you have n times capital T unknowns in these LMIs. So if you have a very large data set, it is going to be more difficult to solve these LMIs. Therefore, somebody should do something better. And there is indeed something better. Another LMI, positive definite P, positive alpha, some L, and this is the LMI. And as you see, P, alpha, L are unknowns. All the rest are data matrices. And if these LMIs are feasible, then LP inverse is a stabilizing feedback. But let's now count the number of unknowns. The number of unknowns now does not depend on the data size, but depend only on the system size, the number of states, the number of inputs. And you cannot go beyond that because already the size of the system, of course, limits the number of unknowns. So imagine if T is very large, this is going to be much, much larger than the number here. So these are even more friendly LMIs. But basically then, if this door is open, somebody rushes in, says, okay, I have this data, can you please, I just open my laptop, write down this LMI. If it is feasible, I am there. If it is not, then I try to calm the person down, like, sorry, we cannot find a stabilizing feedback. So this was about stabilization. Now, as I said before, per problem, conditions on data change. Well, we have seen it in the analysis part. For different problems, we have different conditions. Sometimes identifiability is required. Sometimes it's not required. But basically, per problem, we study data informativity. Now, I'm going to study linear quadratic optimal control because there was a request, and I typed these slides in the break. No, I already had typed them. But there was a question about LQR. So first I want to explain the optimal control problem I want to look at, because there is also a misconception among control people that LQR is very easy and there is a unique solution for the Riccati equation and so on and so forth. Sometimes even in textbooks it is written in that way, but it is not so. And the data part is going to be quicker. But let me explain what I mean by what kind of LQR problem I'm going to look at. I start with a linear input state system, and I have this cost. Q is semi-definite, symmetric semi-definite, R is symmetric positive definite. And as you know, the idea is to minimize this cost. But there is a very important issue. It depends on whether you require, the solution of this problem depends on whether you require x tend to 0 asymptotically or not. So I'm going to look at the zero endpoint problem, in which not only I try to minimize this, but I have this extra constraint that x tends to 0 as t tends to infinity. If you drop this assumption, then it's a different problem. And in principle, these two problems do have different solutions. And that is a point that is missed very often in the literature. So I look at LQR with 0 endpoint. X tends to 0. Okay. I want to minimize it. Well, we study LQR problem in continuous time. This is a discrete time version, but you wouldn't be shocked if I tell you that it is a Riccati equation that needs to be solved. And so then this LQR problem with 0 endpoint is solvable if and only if AB is stabilizable, some observability condition of QA on the unit circle, sorry. And if these are satisfied, then one can prove that there exists a unique largest positive definite solution, P plus of this discrete time algebraic Riccati equation, in the sense that P plus would be greater than or equal to P for any real symmetric P satisfying the Riccati equation. And for every x0, there is an optimal input U star, and it is given by this feedback law where K is computed from the solution of algebraic Riccati equation A, B, and R in this way. And on top of it, A plus BK is stable. These are all from the model-based theory and nothing to do with data-driven yet. It's a recap of LQR with 0 endpoint.
What is the largest positive semi-definite?
So it is largest in this sense. It may have multiple symmetric solutions, and P plus is the largest in the sense that P plus minus P is semi-definite, and it is unique. And I'm going to say that LQR, AB, QR is solvable. If it is solvable, I'm going to say that K is optimal feedback gain, K given by OFG here. Okay? And again, I start with the usual setup, input state system, input state data. This is the set of data consistent systems. The true unknown system is one of them, but there may be many. And I define now the data to be informative for optimal linear quadratic regulation, as I defined in the previous slides, if there exists a K such that this K is optimal feedback gain for any AB. Q and R are fixed. So if this K solves the optimal control problem for every AB data consistent. Okay? So what is your guess? Do we need system identification or identifiability or not? Yes, there is an observability condition that needs to pop up, show up itself, show itself in the conditions. That's a very good guess, because it was not a yes/no answer. The answer is in the middle, and indeed A needs to be identifiable. Yes, very good. Very good intuition. The data are informative if and only if one of the two following conditions hold. This is really, in a way, interesting, because I have never proven anything in my life with this kind of flavor. Two conditions, one of them needs to hold, and they are also completely apart from each other. The first one says that the data are informative for system identification, but then we are done, right? And the second one says that A part needs to be identifiable, B part does not need to be identifiable, but there are more. AS needs to be stable, and Q times AS needs to be 0. And in that case, K is 0. But I have to say that this B is a little bit of, it is a pathological case. And it is because of something deeper sometimes we forget. Some of the discrete time systems you cannot obtain as discretization of continuous time systems. If you use zero-hold discretization, in the discrete time, A matrix would be always non-singular. But if we start from a discrete time system, we do not impose that. Therefore, we are looking at a larger class of systems than one can obtain as a discretization from continuous time systems. And that is, this is exactly because of that, I believe. Okay? And how do I prove it? I'm not going to prove this because this really takes some time, but I can tell you the crux of the proof. The crux of the proof is, well, for given AB, I can write the algebraic Riccati equation. And since K needs to be the same for all AB, one can prove, and this is the K, one can prove that this solution of the solution of this algebraic Riccati equation does not depend on the choice of AB. That is the crux of the proof. Once it is proven, the rest is easy. Okay? So I have another R, right? I have 4 more slides left. Okay. There is one more thing I want to say about optimal control, of course, this doesn't say how we can find the k from data. Well, you can write a semi-definite program to find k. And you can try to maximize trace of p subject to these constraints. This has a unique solution, and it gives you the solution of the algebraic Riccati equation. And the nice thing is, this depends on the data only. And I don't have A, B, I have the data. So this is the way to solve optimal control problem. Okay? And if there is a P plus, then you choose K in a certain way. Okay? Now, here is what we have done. We are interested in exact data to begin with. On the analysis side, we looked at stability, controllability, stabilizability, stability again, but with input state data, observability. And on the design side, we looked at stabilization by state feedback and LQR. But there are many more, even more than what I listed here, problems which are solved in this framework by us or by others. And this is a partial list of all these problems. In the lecture notes, you see you can access most of them. By the way, it would be nice if we have an email list for all the participants, because soon, in a month or two, we are going to finalize the book, and then we can share the entire book. What we shared is part of the book, a large part, but nevertheless not the complete book. Okay? And so one can look at suboptimal problems, optimal control problems. One can look at stabilization by dynamic feedback, and this is the data type. I was interested in input and state data, but one can look at even input-output data. So you can do whatever one can do in model-based theory in this framework for data. Okay? But as I said, this was about exact data. So the last bit of today's presentation, I want to give an overview from mathematical point of view to connect it to noisy data. Let's think about input state systems. So we have this set of consistent systems, data consistent systems. In the exact data case, this set is an affine set. It is a set of solutions to a linear equation. It is a vector in this space. This belongs to Rn times n cross Rn times m. If you treat this as a vector space, this is just one element of it. And this set is going to be then one vector plus a subspace. If I depict it in 2 dimensions, of course, it is not fair. It is going to be something like this, a shifted subspace. Okay? So essentially, in data informativity, from mathematical point of view, what we do is to find conditions under which this affine set is included in another set. For instance, in the set of all controllable systems for controllability. But all controllable systems have an interesting geometry. They are not convex, they are dense. And it seems that it is possible that a affine space can be in that set. But when it comes to design problems, then it is not about a B set, but there is also the K. If you fix K and look at A plus BK and require A plus BK to be stable, that is not even a convex set. But we want this affine set to be in that convex set parameterized by K. For each K, there is 1. And we want to put this affine set into one of them. And it is possible, apparently, only if that A plus BK is a singleton. So this is the way one can look at from mathematical point of view. For the exact data, set of data consistent systems is an affine set. And depending on the problem, I have another set. And I am trying to figure out conditions on data so that this affine set is included in the other set. Okay? And it requires different type of, it requires a certain type of mathematics. As you can remember from the proofs, I take a data consistent system and create yet another one, actually a bunch of them with a parameter alpha, take alpha to infinity and so on to make conclusions. That's the type of mathematics we used so far. When it comes to noisy data, we are going to look at a setup of this form, again, in state input systems. But we are going to add a noise term. W. Well, true system is unknown, but also the noise is unknown. Obviously, one cannot do anything without assuming something on the noise, because if noise is arbitrary, every system is a data consistent system and there is no hope. So what is a reasonable assumption on noise then? Well, I would say something like an energy bound. If I collect all these unknown noise terms, W in a matrix W minus W minus transpose less than or equal to some positive number times identity means that the noise samples are small. Okay? I can write down then this relation now. And Henk is going to, of course, go over the details. I'm just giving a flavor for tomorrow's lectures. Then I can write this data consistent systems. But the required mathematical tools are different now because these systems are going, these sets are going to be ellipsoids rather than affine sets. So one needs to develop some tools for in which we have these ellipsoids and then they are included in other sets. So that is going to be That's going to be the high-level explanation of noisy data, but we will see the details tomorrow. Any questions?
In the LQR case that you did, that was a direct approach, right? The LQR controller that we showed, that was a direct approach.
Yeah.
But you could, so you formulated that as an optimization problem. But you could also do an indirect approach because the condition, the identifiability condition has to be
Yeah.
true.
Yeah.
And so then you could replace A and B in that expression for K
Yeah.
by their data-driven equivalent.
Yes. Yes. True. I mean, true in the sense that this B is a pathological case. If I forget about B, then of course it says you should be able to identify the system. Then I would identify first and solve the Riccati equation. But if I want to treat both A and B, although B is a very pathological case, if I want to treat them equally, then I can also alternatively solve this optimization problem. But I mean, LQR is not an interesting problem, that much interesting problem in terms of data-driven control. Everyone is hungry, of course. All right. Thank you very much.